All right, mixed Anovas. So mixed designs that mix between and within, or between groups and repeated measures. So mixed designs, the term mixed has been used in lots of different ways to describe certain research designs. But in this context, you're going to be talking about mixing between groups and within groups designs, or between groups and repeated measures. So we're going to talk about how to sort of conceptualize the design and sort of types of mixed designs. We'll go through the assumptions. We'll go through the analyses, both deviation and computation, and talk about sort of higher order mixed designs and how that affects calculating the errors and which errors go with which effects. And then once you have significant effects, sort of how to break them down, how to figure out where significant effects lie. So this is a very popular design because it combines the benefits of each, and a lot of things that we like to test sort of match really well with this type of design. It requires that you have one between groups, IV, and one within subjects, or if you like, one between groups and one repeated measures. It's often called a split plot design, which comes out of agriculture, where they literally take a plot of land and split it up, and then plant different plants or do different types of fertilizer or something in it, so that you have the land being the repeated measure part, and then the different treatments being sort of the between groups components. So it literally is like splitting up a plot of land and testing out different things with it. So it's kind of like a split plot design is where the term comes from. The thing about mixed designs is that the simplest form of mixed design is essentially factorial. There's no one-way mixed design. You have to have at least two variables. So it's, in the simplest form, it's going to be a 2x2 design. So this is a example of a simple 2x2 where you have the Kaplan and Princeton here. This is sort of the between groups component of it, and then up here the GRE before and after is the repeated measures. The idea being to see if subjects change more or less given the two different treatments. You could even think of this having a third treatment that would be sort of no training. So Kaplan is a GRE training course, so is Princeton. You could have another group that does nothing in the same time period, and that would sort of tell you if the two treatment groups change different or better than the control. It's pretty straightforward. The advantages here is that it allows someone to generalize a repeated measures effect over the randomized groups part. So let's say you get no interaction. Well, it tells you that the change you're getting in the repeated measures is actually generalizing across all the groups. That can be good. That could also be bad, especially when it's bad when people want there to be an interaction, or one group is changing faster than the other. Like if you have a treatment control, you want the treatment group to change and then the control group not to. So in that case, you don't want them to generalize. But second, you get reduced error because in the repeated measures component, you're still able to identify the repeated measures. In the repeated measures part, you're able to identify the consistent scoring of people and remove that from the error, so that you can actually reduce the error down, but not quite as much as if it's purely repeated measures. The disadvantage is that it sort of adds together the complexities of both. The short story there is you have to keep track of what errors go with what, and it's not quite as straightforward as it is with either purely between or purely repeated measures. You now have to sort of figure out what errors go with what effects. That can be sometimes tricky. So, in terms of types of mixed designs, really anytime you're mixing together, between groups IVs and repeated measures IVs, you have 5 repeated measures, 2 between groups, you have 5 between groups and 2 repeated measures, whatever. Any mixture of those is going to be a sort of mixed ANOVA. One in particular that it comes up a lot is this design here that's called a pre-test, post-test. It's a pre-test, post-test, control group design where you have a treatment group and control, where the treatment group gets a pre-test and a post-test with a treatment in between, and the control group gets the pre-test and post-test with no treatment. And this helps to assess for things like testing, because if the treatment really isn't working, so if the treatment here is not working very well, then you expect the control group to change as much as the treatment group. Because if there is a testing effect by simply pre-testing these subjects here, you'd expect them to change because of the testing. Well, now you can see that these subjects change more than the control group, and that difference between those two groups will tell you what the real effect for the treatment is minus the testing effect. So it's a way to control, control the testing effect in these kind of pre-test, post-test designs. In terms of the general linear model, you can sort of see that the way this sort of works out, this is the up here in the regular factorial, you get your mu plus alpha plus beta plus alpha beta, which is the interaction, and then all the errors rolled up into one sort of randomized group's error, which typically in a completely between groups, this is S within AB, right? In a mixed design, all the effects outside of error are the same. You still have mu, you still have alpha, the effect of A, whatever that effect is. You have beta, and you have the interaction. We sort of draw a line here where everything, the alpha and S, so this is sigma, lowercase sigma within alpha, these two components here are the straight sort of between groups parts. And everything down here is anything that includes or repeated measures. So the effects for alpha, beta, and the interaction, they're really the same effects. It's just we've taken this S within AB effect and we've split it into this error, that's the repeated measures part, and this error, that's the between groups part. We've now sort of separated out what corresponds to the between groups, which is just this one error here, and what corresponds to both beta, which is repeated measures, and the interaction, because even though alpha is between groups, because beta is repeated measures and you have at least one repeated measures factor, it turns it into a repeated measures component and it gets the same errors. This is usually referred to as B by S with an A. So it's beta by sigma and all that's nested with an A. So all that's sort of stated down here. Alpha, beta, and alpha, beta are essentially the same thing. They're all main effects. S with an alpha is a deviation of scores caused by consistent subject differences, effects of the S that are nested with an A. Before, we only had one set of S's. So now those set of S's, we can still get consistent scoring, but we have to look at how those subjects score consistently in the between groups, like A1 and A2 and A3 and stuff separately, and sort of average across them. So it's now the average consistent scoring of subjects across the between groups. And then the beta by S with an A is how the B factor, the B variable, interacts with that consistent scoring, or with the subjects nested within each A level. me go back a second. Even like here, the reason why these subjects, like 1 through 5, right, they are nested within, so all these subjects are nested within A1. This is A1, right, and this is A2. And you can think this up here is B1 and B2. So all these subjects 1 through 5, are nested within A1. All these subjects are nested within A2. So when we start thinking about the S within A effect, we have to sort of average that consistent error across the A1 and A2 groups and get a consistent S within A effect. And then as B goes across, going B1 to B2, we're going to get the interaction between B and this consistent error over here, the S with an A, is going to be our error term. How does the B effect interact with subjects while those subjects are nesting within A? All right. The assumptions, really, we don't have to spend a whole lot of time talking about them, but they're the same assumptions as all the other Anovas. The between groups component has the between groups assumptions, and the repeated measures component has the additional sphericity assumption. So we're assuming everything is normal. The normality of sampling distribution in the between groups IVs. So it applies to the case averages, because remember, we're going to be averaging those subject scores in order to get that S with an A factor. So it applies there. We're assuming homogeneity of variance. It applies to every level or combination of levels of the between groups IVs. Right. So it applies the same way it would be for a one-way or a factorial between groups. So we're going to check for homogeneity of variance. We're going to assume things like independence. Right. So in the between groups part, we're going to assume that all those subjects are actually independent. Going across the repeated measures, we can't assume that because it's the same people going across, but we can assume that for the subjects in that are in different groups. So the between groups error does assume that everybody's independent, but each repeated measure error term confounds random variability with the subjects by effects interaction. So, on any repeated measures factor, we want to know that the change in mean is sort of separate from a change in variance or spread from one to the other. Really a spread of the change across the time points. So we need to test for sphericity instead. The test is on the average variance covariance matrix, like over the levels of the between groups IV. So this is where things get a little more complicated. It's not super necessary to go into detail, but it's really talking about, we want to test for sphericity. We want to be able to look at the differences between groups. Difference in this case between times. But to do so, we're going to average over the between groups in order to do that. We're assuming there's no outliers. For a number of reasons, those affect the mean, and they also affect, our generalizability. We're trying to test for a specific type of person. If there's somebody that doesn't belong in there, well, then they shouldn't be in there. They're an outlier. Whether their point is far away or whatever, they're an outlier if they don't really belong with that group of folks. Missing data is the same issue we have in any repeated measures component. The chances for missing sort of increase, so we get to be sort of thinking about that, and they cause different problems depending on if across the between groups or within groups, because across the between groups it really is just an unequal n issue. You meant to run 10 people in each group, but you got 8 in one and 9 in the other. That's really just an intention problem. You intended to run a certain amount and didn't, and it also can affect power. Across time, we're talking about sort of attrition, people sort of dropping out. They started in the study and then dropped out, so it's a different issue. So data points missing across the within subjects or repeated measures part can be estimated as discussed previously. Because you have other points that they've scored, it's not too hard, too difficult to make educated guesses or mathematical guesses of what their scores would look like. Missing data on the randomized groups part causes sort of non-orthogonality, again, because there's different numbers of different ends across the groups. So there are different issues and they cause different problems. So let's talk about the analysis, right? So let's say we have randomized groups with 3 levels, A1, A2, A3. And within groups, we have B1, B2, B3. And it's important to sort of clarify this because the equations that we're about to go through would look differently if B were the between groups or randomized groups and A were the within or repeated measures. Then we would write them differently. The equations would come out different because of which one is repeated and which one is between groups. So we're going to specify that A is the randomized groups, B is the repeated measures, and sort of talk about the deviation form from there. So the sources of variance, all of them start off sort of the same. There's total variability, there's variability that's due to between groups, and there's variability due to within groups. So what effects actually do exist in here? Well, the between groups parts are sort of the same, right? So it's A, B, and AB. Right. The within groups part, we have an S within A, right? Because all these subjects are sort of nesting, right? They're going across the B levels, but these folks are the same folks they're only in A1, so they nest in A1. These folks nest in A2. These folks nest in A3. So we have an S within A, and then we have a B by S within A. So we're going to have A minus 1, B minus 1. These all look the same. A minus 1 times B minus 1. And then here we're going to have an A times S minus 1, which gives us A S minus A. And here we're going to have an A on the outside times B minus 1 times S minus 1. So we factor that out. That's B S minus B minus S plus 1. And then as we've distribute the A out, it becomes ABS minus AB minus AS plus and then A again at the end. So the example that's in the Tabachnik Fidel book is the same sort of books by month example, but instead of having the same people read, books across months, if we designed the previous research study concerning reading different novels over time, but instead of having everyone read all the books for all 3 months, we randomly assigned subjects to read 3 different books and have them read for 3 months each. So it looks like this. So we assigned 5 people to read science fiction, a different set of 5 people to read mystery, and yet another set to read romance across 1, 2, and 3 months. So this ends up being a 3 by 3 mixed design, where novel this is between groups. It's weird to write sideways. This is between groups. This one's repeated measures or within groups. And you can see, like any repeated measures, we have case means here because the same subject scores 3 times. So we're able to actually get a mean for subject 1. And then we can get a mean for A because those 5 people have a mean of 5.2. If we actually average their means down, we got a mean of 4.2. We can average these subjects down to have a mean of 2.8. we can average these subjects down to have a mean of 2.733. I can also get a mean for all of month 1, which is there, all of month 2, all of month 3. And I also have the individual cells, which is these means are all the cell means, looking at the different months at the different books at the different months. So you can see how this looks like 3x3 factorial design. The only difference is because we have subjects that repeat, we're actually able to look at case means. We can actually then figure out how the consistent scoring sort of plays in. All right. So this is the sort of average data. We're averaging across subjects, we're averaging across cells, across levels of B, levels of A. To get everything averaged, we can look at the sort of deviation approach. So looking at this, this corresponds to the GLM part. Obviously it doesn't have the mu in it, but here's the effect for A, the effect for B, the effect for interaction. Here's the subjects nesting with an A, and here's B interacting with those subjects nested with an A. These parts, the first 3 of these, again, are exactly the same. Matter of fact, whether you're doing this as completely between groups, completely repeated measures, or as a mixed design, the way you find A, B, and AB is the same. What's different is the parts over here change depending on whether you're only going to do these types of errors if you're looking at a mixed design. So here we have each subject and each of the cells, A and B cells, minus the grand mean. Right? Here we have each of the A means, because this is I, and this is A and B. So I want 1 for every A level, but I want to average over I and K to get 1 mean per each of the A levels. Let's go back a second. So we're talking about these. 1 mean for each of the A levels. We're talking about these means there. Alright. Now we're going to subtract the grand mean, and we're going to multiply by the number of people it took to get there. So these scores here, we're talking about averaging. Now this is going to see, this will be interesting. We're going to average, there are 5 people in each of the cells, but I think this average really is the average of all 15 here. So it's going to end up being 15 here. We're going to do the same thing for B. This is now the mean of each B level, because we're averaging over I and J. So this is the mean for each B level, minus the grand mean squared, and multiplying by the number of people it took to get each of those B levels. So now I'm talking about this B, that B, and that B. And that is the average of these 5, those 5, and those 5, right? So we're talking about 15 people there as well. In the brackets, right, whenever you see brackets like this, should tip you off there's an interaction of some sort. So this is the mean of each individual cell, right? So we're averaging over I, but doing it for every JK combination, and I'm subtracting out the grand mean. So that means I'm taking each of the cells here, 2.4, 3.8, 6.4, 4, 3, 1.4, 3.6, 3.2, 1.4. In fact, I'll change colors here just for the. So now I'm talking about each of these cells. All right, each cell mean around the grand mean. But the differences between these 9 cells also includes differences between the repeated measures component, right, and the A components here. So we have to subtract them back out. So this, go back to red again. So this is the cell means around the grand mean, minus, this is now my effect for, this is now my sum of squares for A, and my sum of squares for B that I'm subtracting out. And in the end, this whole thing gives us, if I do all that, it gives us my sum of squares for A, B. I don't know why that disappeared, that was weird. Right, so the thing in the brackets here, sum of squares for A, B. Okay. This is each individual averaged over A and B. Right, the J and K levels of A and B. This is every subject. And I'm subtracting out the mean of each A level. Right, so this is I and K are being averaged over, but I want 1 for every A. So now I'm taking each, actually you need a different color. Choose green. So now I'm taking each of the cell means around each of the A means. Right, so I'm doing that 1, 2, 3, 4, 5 times. And then when I get to the 6th person, I'm switching over to this mean and doing it 1, 2, 3, 4, 5 times. And then when I get to the 11th person, I'm switching over to this mean and doing it 1, 2, 3, 4, 5 times. So if this were, if this were just a one-way Anova, with the, this would look like a one-way Anova, and we're getting the S within A effect, right? The typical one-way Anova within groups error term. That's all I'm doing here. Just doing those 5 subjects around their own group, right? So now we give me sum of squares within groups. So that's this part here is my sum of squares, S within A. Here, let's use a different color. Purple. So here we're talking about each individual and every J and K combination. So this is really every score. I'm subtracting out from that the average of each cell, each J and K combination. So this first part of this is I'm looking at every individual score, like 1 minus the cell mean. I'm doing that 1, 2, 3, 4, 5 times, all around 2.4. Then switching over here, doing it 1, 2, 3, 4, 5 times, around 3.8. And then 1, 2, 3, 4, 5 times, all around 6.4. So 6 minus 6.4 squared, plus 8 minus 6.4 squared, and so on. I'm doing it over here, 1, 2, 3, 4, 5 times around this mean. 3, 4, 5 times around this mean. 1, 2, 3, 4, 5 times around that mean. 1, 2, 3, 4, 5 times around this mean. 1, 2, 3, 4, 5 times around that mean, and then 2, 3, 4, 5 times around that mean. So I'm doing it once for every single person. Now typically that would be, if this were a between groups design, that would be simply the sum of squares of S within AB. That would be the complete S within AB sort of effect. But because it's repeated, there's a repeated measures component here, and we found how subjects sort of are nesting within A, we have to subtract that part out. So to know how subjects, to get the entire thing, so this whole thing here, really this whole thing is our sum of squares of B by S within A. So to get that, I'm finding my sum of squares S within AB. And subtracting from that, this is the same thing as this, same thing here. This is my sum of squares S within A. And what I'm left with then is that. And you can see, because this is in brackets, this is yet another interaction, B by S. B interacting with subjects while those subjects are nesting within levels of A. Alright, so I know it's a lot. We talk about, this, going through this oftentimes I think it's tedious, but one thing I did that I added to the lecture is this sort of page here, just to give us an idea of what goes where and things to be concerned about. So let's look at this laser pointer. Okay. So the main thing to keep in mind when you're talking about the actual effects themselves. So I say all the main effects that you're calculating in the interaction, they're all the same. A, B, A, B for between. A, B, A, B for repeated. A, B, A, B for mixed. And how you actually compute them, whether it's deviation or computation, is exactly the same. So there's nothing new to learn. This is all the same. This is all the same. This is all the same. They're all the same. We find them the same way. Where things change is how the sort of errors sort of correspond. When you do something that's completely between, you get one error term, subjects nesting within AB. That's it. Right? Because the subjects nest within each cell of the design, and because it's completely randomized groups between groups, there's no repeated measures, we can average across all the cells and get a single error term that is subjects within the AB combinations. For repeated, we have to calculate this extra S, that's the consistent scoring, and then every single effect, A gets an A by S effect, B gets a B by S effect, and AB gets an A by B by S effect. And that's because once we account for the sort of consistent error, the rest of these are all interactions between the effect and subjects. So this is the effect of A with S, this is the effect of B with S, and this is the effect of A by B by S. For mixed designs, it gets tricky. So because we consider A to be completely between, it gets its own error term of subjects within A. So the between groups component gets a between groups error. Now B and AB, because it includes B, they're considered both repeated measures components, B and AB. Because they're both repeated measures components, they both get the same error. So they're both going to be covered by B by S with an A. So they're both repeated, they get a repeated measures error term. So the between gets a between, and then both of these get a repeated measures. Now, this may sound a little bit confusing, but the nice thing is, with between, we had basically, if we don't count total, we had 1, 2, 3, 4 effects that calculate. With repeated, it went from 4 to 1, 2, 3, 4, 5, 6, 7 things to calculate. And now we've dropped back down to 1, 2, 3, 4, 5 things. So this is closer to the between, in terms of this has 4 and this only has 1 more, 5. They're different, right? But it's still just 5 errors as opposed to having to calculate all 7 of these things. So that's something nice there. What mixed designs lack is this sort of symmetry, or there's a sort of beauty where everything, like A gets its own error, B gets its own error, AB gets its own error. So with repeated, there's a sort of one-to-one correspondence that's kind of nice. With mixed, there is a bit of trying to figure out what error goes with what effect, and that can be kind of confusing. For S with an A and SSS with an A, you really think about sort of dropping this whole thing down to just this one case. Now this is not like with repeated measure where we have to remake the whole data set, because this has already been made for us. It's just the case means. But you can think of it for A and for S with an A as if we're treating this as a one-way Anova with just the case means and the means for each of the A levels as our subject scores and means, right? That's all we really need. So we're going to use just those. Oops, did that wrong. This is supposed to go there, and that's the mean. So we can just think about just using those components, and we don't need the rest of it. Alright. So let's look at this. So this says n times the mean of each group minus the grand mean. So we're talking about these means here all around this grand mean. So this ends up being pretty easy. It's just 4.2 minus 3.244 squared plus 2.8 minus 3.244, sort of, etc. We're going to weight these. So where it gets a little bit weird is each of these five scores, or these 5 means, is a product of 3 things. So we're actually going to weighting this by 15, not by 5 the way we normally do, because each of these means really is the mean of 15 scores. Same thing down here when I'm doing the means of each person around the group mean. I'm talking about doing 3.333 minus 4.2 squared plus 4.333 minus 4.2 squared, sort of, etc., all the way down to like 3 minus 2.733 squared plus 2.667 minus 3. The wrong mean. Minus 2.7733 squared equals. So we're going to do that, really doing it 15 times, and then out here you're going to be multiplying the whole thing, because each one of these scores is the product of 3, is an average of 3 scores. We're multiplying this by 3. That's why it's got the K out there. Alright, so this is multiplying this by 3 all the way through. For B, we now are looking at these means here around the grain mean. So we're talking about 3.333 minus 3.244 squared plus another 3.333 minus 3.244 squared plus, and the last one is 3.067. 3.067 minus 3.244. It's a little bit more straightforward that there are, 5, 10, 15 things going in there, so we're multiplying this by 15 as well. Alright, to get our B. And for AB, we'll be looking at each of the cells. Right, so 2.4 minus 3.244 squared plus 3.8 minus 3.244 plus, and keep doing that. Let's skip down to the last couple. Like 3.2 minus 3.244 squared plus 1.4 minus 3.244 squared. Right. All that's going to be multiplied by, there are 5 in each cell, so we're multiplying that by 5. Once we get this really gives us our sum of squares between groups, like all of it. Right, that's what this equals to. So once we get this, to get my sum of squares AB, I gotta take this thing, the sum of squares between groups, subtract out the sum of squares for A, subtract out the sum of squares for B. which we already found, here and on the previous page. Subtract those out and you get the sum of squares you're looking for. Alright. For b by s with an a, we're not talking about going through each individual score, because this here really is the sum of squares of s within AB. Right? I don't want that though. I want sum of squares of b by s with an a. So I'm going to take this, subtract out the s with an a, and what's left is the b by s with an a. So this is again 1 minus 2.4 plus 1 minus 2.4 squared plus 3 minus 2.4 plus 5 minus 2.4 squared. It's going to keep going all the way through the next group, all the way through all these groups, subtracting out their group mean to get down to the bottom. Let's do, last couple we're going to do 1 minus 1.4 squared plus 2 minus 1.4 squared. And the nice thing is there's no need to multiply anything, with each one of these is an individual score, so we don't need to multiply anything. You're going to go through each one of those, doing it 15, 30, 45 times. And in the end, you'll get your sum of squares s within AB. But to get my sum of squares b by s within a, I'm going to take that sum of squares s within AB and subtract out my sum of squares s within a. Okay? And total is the same all the time. Each score 1 minus the grand mean 3.244 squared plus 1 minus 3.244. Do that 45 times. What? Do that, like I said, 45 times. With the last one being like 2 minus 3.244, right? Squared. Add all that up, and you'll have the total. Looking at SSA, you can sort of see where this So here's our A1 mean, or A2 mean, or A3 mean. So that's what the 4.2, 2.8, 2.773, all subtracting out the grand mean and multiplying by 15, because each one of these means really is the average of 15 things. It just looks like 5 because each one of these 5 things is the average of 3 things. So 3 things averaged and then averaged again 5 times gives us 15 different numbers being averaged to get us our group means. We're looking at S with an A. We're going to compare each one of these subject means to their own group mean. So that's why it goes 3.333, 4.334, 5.667, 3.667 for the first 5, all subtracting out 4.2. And it goes 1.333, 3.333, 3.333, 2, 4 for these 4, all subtracting out 2.8. And then 2, 3, 3, 3, 2.667. All these all subtracting out the same mean of 2.733. Looking at the sum of squares for B, Now I'm going to take these three means here. I'm just going to switch it back to laser pointer. Alright. Alright, so here's 3.333, 3.333, and 3.067. That's where these numbers come from. 3.333, 3.333, 3.067. All subtracting out the grand mean. And weighting by 15 because there are 5, 10, 15 scores being averaged. Alright, now once we have, and it ends up being this really small 0.708 number. So once we have all that, for AB, we're going to take each of the cell means, 2.4, 3.8, 2.4, 3.8, 6.4, 4, 3, 1.4, 3.6, 3.2, 1.4. Those are all 9 of those cell means to get this sum of squares between groups. I'm going to take that, subtract out the sum of squares for A, which is here, the 20.583 number, and the sum of squares for B, this 0.78 number. Subtract both those out, and what's left then is my interaction. Okay. For B bias with an A, I'm going to take each individual score. Right, subtract out the group mean, the cell mean. So that's why it's going 1, 1, 1, 3, 5, 2. 1, 1, 3, 5, 2. 3, 4, 3, 5, 4. 3, 4, 3, 5, 4. 6, 8, 6, 7, 5. 6, 8, 6, 7, 5. So for the first one, I'm subtracting 2.4 out each time. For the first group, that's their mean. Then I'm subtracting out 3.8, because that's the second group's mean. And then 6.4, so the third group. And then 4 each time, because that's the fourth. And then 3 each time, well, that's this group. And then 1.4 each time, because that's this group. And 3.6 each time, because that's this group. 3.2 each time, because that's this group. And 1.4 each time, because that's this last group here. When we do all that, what this gives us here is really the sum of squares for S with an AB. So I'm going to take that number, subtract out the sum of squares for S with an A, which is here, 26.4. Alright, subtract that out from it. When I do that, I get this 37.2 number, which is the real sort of sum of squares B by S with an A error term we want for our repeated measures component. Right, so I just sort of did it twice. I sort of slowly went through it by hand, and then walked through it. The equations all laid out here, so that you got sort of 2 looks at how it goes. And these equations are they're laid out a little nicer. It's definitely nicer than my handwriting. So hopefully taking 2 trips through that actually helped. For total, we're taking each individual score minus the grand mean. So that's why it's 3.244, and every single one of them, I'm going 1, 1, 3, 5, 2, 1, 1, 3, 5, 2, and then 3, 4, 3, 5, 4, 3, 4, 3, 5, 4. So I'm just going every single score, and it all adds up to the 156.311. So that's the deviation approach. Alright, so we have the sum of squares. If you want to get the sum of squares computational route, we need to look at the degrees of freedom and convert them. Same process we did before. So we now have the things you got to keep track of are A, B, and S. So it's going to be the sum of AJ squared over BS minus T squared over ABS. This is going to be the sum of AJSI squared over B minus the same as above there, sum of AJSI j squared over bs. For b, it's going to be the sum of bk squared over as minus t squared over abs. Here we gotta multiply all out, so ab minus a minus b plus 1. So that becomes the sum of a j b. Oops, I missed the sum. Sum of the sum of a j b k squared over s minus the sum of a j squared over bs minus the sum of bk squared over as plus t squared over abs. Here we got to expand the b minus 1, s minus 1 part in the same way. So that becomes bs minus b minus s plus 1. And when we distribute the a out, it becomes abs minus ab minus as. And instead of plus 1, it's now plus a. So abs becomes sum of y squared. So it's going to be sum of y squared minus the same thing up here, the sum of a j b k squared over s minus the sum of a j s I squared over b plus the sum of a j squared over bs. And then for total, sum of y squared minus t squared over abs. That's it. They expand out in the same way we normally do. They follow all the same rules. Instead of having to, using the means of each cell, the means of each person, means of each A level and B level, we're using the sums instead, and we get the little extra sum of, I don't want to cross it out, I want to circle it, the sum of y squared value there, and the total instead of the grand mean. With all that, we can actually go through and figure out all the components. Again, whenever we're looking at sum of squares for A and sum of squares for S with an A, we're really focusing on just the case totals. B can actually sort of be ignored for that. You don't have to do anything. We're really just sort of honing in on, let's just look at this one column and sort of leave this out for we're looking at A and S with an A. We don't need to look at B, so we can just look at just the case totals. Right. For the sum of AJ, so we have these sums. So it's going to be 63 squared plus 42 squared plus 41 squared all over, it's BS, so that's B has 3, S has 5, so that's over 15. Notice that we're dividing by 15 here the same way we multiply by 15 in the deviation approach. Minus T is 146, 6 squared over ABS, which is 3 times 3 is 9, times 5 is 45. Alright, we'll go through the actual calculations in a sec. Just sort of helping to write this out. So the AJSI are these values here. There's a lot of those over B. So we're talking about 10, 13, 12, 17, 11, 4, 10, 10, 6, 12, 6, 9, 9, 9, 8. It's supposed to be 12. So then we're just squaring and adding those up. Let's just sum all those up. It's going to be divided by 3. And subtract out the same, 63 squared plus 42 squared plus 41 squared over 15. To get the SSS ordained. Okay. Again, we'll talk about the actual calculations in a sec. When we go, like I actually have it written out, we can look at it that way. For B, looking at these 3 here. So, 50 squared plus 50 squared plus 46 squared over AS, still 3 times 5 is 15. This is still going to be 146 squared over 45. Alright, for AB, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 sums. So that's 12, 19, 32. Let's do it this way. 20, not 12. It's weird, I said 20, my hand wrote 12. 20 plus 15 plus 7, 18, 16, and 7. So this is all squared plus squared plus squared. It's going to be over S, which is 5. Let's subtract out the component for A here, the component for B here, right? We already found out. And then plus the, 146 squared over 45. This component is this, right? And this component is this. And again, we'll talk about what those values are in just a second. For B by S with an A, it's going to be 630, which is sum of y squared, minus the AB component, minus the A component, minus the AS component, minus the A component. This way. So 630 minus AB. So AB is this thing. AS, we haven't done yet. Oh no, we did. AS is this whole thing, right? Yeah, and then A, we also did. It's this thing, right? So we already figured them out. And then for the total, it's the 630 minus the 146 squared over 45. Alright, so let's look at that stuff filled in. So here's our 63, 42, and 41 squared over 15. Ends up being this 494.267. 146 squared over 45 ends up being this this 21,316 over 45. Ends up being this 473.689. Alright, so here's our sum of squares for A. for S within A, here's all those individual means, 10, 13, all this stuff, all squared, divided by 3, ends up being 1562 divided by 3, which is that 526.67, minus the same thing we got for A before, which is up here, right? So we already found it. So let's just go in there. Subtract those out, you get 26.4. For B, we have the 50, 50, and 46 squared, which are there, divided by 15. So that ends up being 7,116 over 15, which is this 474.4, minus the same total squared, which is this 473.689 that we already found here, right? Yeah, so just plugging it back in again, getting this small number. I think when we did it, deviation, it was like 0.708 or something, but it's super close. Sorry. My brain remembering things that aren't true. Yeah, 0.708. Close. For AB, I'm taking each of the cell means here, all squared, added up, divided by 5, ends up being 2,832 over 5, right, minus 494.267. 494.267 is from here, it's the A component, it's this thing here. 474.4 is from here, which is this thing. The plus the 473.689, which is this that we get from the t squared over ABS. All those components. Subtract them out and you get 71.422. Now here ends up being 7y squared minus the AB version. So AB is this thing, right? Which is this whole thing. This number there. Right, 566.4 minus AS, which we found before as well. This thing, which is this 520.667. Just there, right? Plus the effect for A, 494.267. This again here, 494.267. You get 37.2. And here we got the 630, which is given to us there. And the 473.689 is the number that we get for t squared over ABS each time. Subtract those, you get 156.311. So they all come out really close. The only one that's sort of off a little bit is this one, where this is deviation, this is the computation, but they're still all really close. And we have all of the degrees of freedom that we figured out from before, you know, A minus 1, so there's 3 levels of A, so 3 minus 1 is 2. We have A times the subject degrees of freedom, so that's 3 times 5 minus 1, 3 times 4 is 12. There's 3 levels of B, so that's 2 as well. We have 2 times 2 equals 4. Here we have our B interaction between B and S, so that's 3 levels of B times the 3 minus 1, which is B is 2, times the subject degrees of freedom, which is 4, so 2 times 4 is 8, and then 8 times the levels of A, so 8 times 3 is 24, and then of course the total number of subjects minus 1 is 45 subjects minus 1 is 44. 24 plus 4 plus 2 plus 12 plus 2 equals 44, so it all sort of adds up together, which is nice. Everything's sort of working out. Once we get our results, and put them in a similar sort of table. We just tend to group them differently, so we tend to sort of keep the randomized and repeated measures separate, so that when, for everything we're going to be dividing this way to get our mean squares. That doesn't change. But I'm going to divide this way for our f, and now we divide this by this, but also this by this, to get these two f's. Alright, so b divided by the b by s with an a, and ab divided by b by s with an a. So they're both going to get the same one error term at the bottom. And then of course you can test the f's for significance using 2 and 12, 2 and 24, and 4 and 24 degrees of freedom to look at the critical values. With higher order mixed designs, this is where some of the complication comes in. You can sort of see in this table in terms of keeping track of what error goes with what effects. So you can start off here with, here I used the pen. You can start off looking at, so if you're looking here, right, so if all we have is A and B, where A is randomized groups and B is repeated measures, it's pretty straightforward. A is randomized groups, and it gets its own error term, right, S with an A. B and A times B, and that's because both of these include B, right? So it's B with any of the randomized groups effects is going to have the same error. So B with S, B times S with an A. That's pretty straightforward. So what if now? So one of the things to keep in mind organizationally is that the repeated measures errors are going to coincide, so that anything that has the repeated measures variable by itself, or the repeated measures variable with the randomized groups variables, are going to have a single error. So, for example, if we have a three-way mixed design where A and B are both randomized groups, and C is the only one that's repeated measures, what you're going to see is that anything that's completely randomized groups, which is A, B, and the interaction between A and B, those are all completely randomized. It's going to have one S within A, B error. That's it. C, or anything that's C with A, C with B, or C with both A and B, so down here C, A by C, B by C, and A by B by C, will get one error that's C times S within AB. So all of those effects get one error. Alright, now look down here. If instead A is the only between groups, or randomized groups, and B and C are both repeated measures, okay, A is still the easy one. A is the only randomized groups, so it gets its one S within A error. That's it. Now, B and C are treated sort of separately because they're both repeated measures. So anything that's B or B with A, here, B, or A times B, gets B by S with an A. Anything that's C or C with A, okay, so C and A by C gets a C by S with an A error term. And then when B and C are both in there together at the same time, it gets a separate error term, which is the interaction between B and C. And then the three-way interaction between A, B, and C all get this B by C by S with an A error term. You can see how it gets complicated pretty quick. It sort of helps that A and B, right, are both here. B times S with an A. C and A, A and C are both here. C times S with an A. But neither of those have both B and C in it at the same time. So that's why you need a third error term that is B and C times S with an A, so that all of them are included in one error term. So it's like a four-way mix. Let's say you have A and B are randomized groups, C and D are repeated measures. Anything that's completely randomized groups, right? So A and B, A, B, A, B, all get the S with an AB error term. That one's always, the randomized groups part's always the easiest. Anything that's just C or C with either A or B, right, is going to get its own error terms. Right? So C is the sort of guiding factor here. Anything that's C or C with the randomized groups effects will get one error. So that's C, A by C, B by C, and A by B by C all get C by S with an AB. Because realize that all those letters are here, right? So AB is there, so the A by B by C effect is captured here. Right? So B by C, A by C, and all that stuff all is captured within one error term of C by S with an A, because C is the sort of organizing component of that. So again, D by itself or with A or B or A and B is D, A by D, B by D, and A by B by D all get D by S with an AB. The only time that changes is if we have both C and D together, it gets a different error term, which is C by D, A by C by D, B by C by D, and then A by B by C by D all get C by D by S with an AB. Because again, because it has both the repeated measures factors in it, it's a separate error term than either of the repeated measures factors by themselves, like C or D alone. So now, when you have a significant effect that has more than two levels, just like anything, we have to break those effects down. We have to try and look at the main effects, look at interactions, and if the main effect or interaction is completely between groups, right? So everything is only between groups. Like think about here, where you have A and B together, or A and B together here. Any of those effects, A, B, or the interaction, if you want to break those down, you can do it in the way we always have. The comparisons are done the same way as if if the repeated measures didn't even exist in the data. We can always use the F-comp equations to plug in the weights, like if you want linear trend or something, times the means of the between groups variables. Sum, square those, multiply them by n, sum the weight, square them. Or if you really wanted to, and we're doing this through regression, which we haven't even really talked about because it just gets ridiculous, you would already have that sum of squares regression, and you can divide it by the one between groups error. And this works because for the between groups, there's always only one error. It's going back to here again. So this between groups, there's one error. This between groups, there's only one error. This between groups, only one error, right? So all the between groups get one single error. So anything you want to do that's between groups, we can use that single error on the bottom and calculate F's for the comparisons. So, that makes it totally easy. At least relative to the repeated measures. So for repeated measures, if within groups the repeated measures variable is significant, you also need to follow the comparisons, some kind of follow-up to compare the levels. But the within groups comparison is different from between groups variables in that you have to have a separate error term each time you rearrange the data. So that would mean you can't just plug it into an F-comp equation. You have to actually redo everything to get your sum of squares for the effect and your sum of squares for this new error, because all the errors are a product of an interaction between the repeated measures effect and subjects. In this case, subjects nested within the between groups. We have to recompute the error term each time. So instead of the F-comp formula, you would actually just rearrange the data like we did with repeated measures and rerun it. So to give you an example, let's say we have the A effect here is the between groups, so science fiction, mystery, romance, and month is the repeated measures, month 1, month 2, month 3. Let's say we wanted to do a linear trend of month. So if I want to do a linear trend of month, that ends up being the code is for that is like -1, 0, and then 1 or something like that. Right? So what that really means is that we just need to completely get rid of the month 2 altogether. We're just going to say, like, look, for a second, this level doesn't exist, and we have to adjust the case totals, adjust the total and all the different components, like even the sum of y squared would just shift as well. So we need to adjust all those while pretending that this doesn't exist. So looking at this, we basically just reshift it to this instead, with new case totals, a new total. I don't have the sum of y squared here, but there would be a new sum of y squared as well if you're doing this sort of computational form. You'd have to recompute the sum of y squared value 2 in order to rerun it. So all I did was completely just leave out the middle variable and just rerun the whole thing so that I can actually get, I need an s within a, we'll call that sort of star, because it's a new, it's how subjects nest within A and how that interacts with B. Right, so it's a B by S within A. I'm just calling it star because, actually I should put the star really here, B, it's a new B. And how that interacts with the subject nest within A is going to be different than when we had the full 3 levels of B. So that's why this has to be recomputed. And you can get the new effect for B, we'll call it, the B star, and get a new B by S with an A star, and get the sum of squares for those. The pens are being funny. Get the sum of squares for those in order to get sort of an F star for the comparison. Right, so we're going to get an F for the comparison for B that is like for the linear trend, and to do that we're basically calculating a new sum of squares for B by only using these 2 levels, and then calculating the new error term that is the interaction with that new B and subjects with an A. So you really literally just are going to redo the whole thing, leaving out that one level, and then that will give you your test for linear trend across the months. And you would update everything. Notice that the sums for each of the cells are the same, but we're not using all the cells. The cells in the middle are getting left out. Interactions, if the interactions are purely between groups, then do the simple effects, simple contrast, do all the stuff we normally would, use your fcomp, do all the stuff we normally would with between groups. If it's purely within groups, or there's any within groups involved, right? So even if you have 5 between groups variables and 1 within group, you're going to treat it as within groups. So they require a new error term for each simple effect, simple contrast, interaction contrast, all that stuff is going to have to be redone, just pretending like it's a new data set altogether by reorganizing it, right? Because if in our data set, if we have the 3 by 3, right, if I want to compare, look at the interaction between, this is A1, A2, A3. If I want to look at just A1 across as a simple effect here, simple effect. If I want to do that, I'm pretty much just going to run a one-way repeated measures that's going to have a new error term, a new everything. So I might as well just rerun that repeated measures design cross B for A1, same thing for A2, A3. It's going to give us a new effect, and it's going to give us a new error term. So that's why we can't just plug it into fcomp like we do with between groups. We need to do each one separately. That's why I said just leave it to SPSS. You can actually just select out the groups you want, run the repeated measures. Even if you run it if you're doing it this way, it's a little bit different because it's still sort of the same idea. You're going to end up getting a new error term each time and just running it that way. So that's fine if you're doing simple effects either way. You pretty much just got to rerun it. Select the group, select the variable, and just rerun it to get your effect and your error term recomputed as part of that new Anova.